Hi friends, in this video I am going to discuss about the concept of the differential length, area and the volume in case of the cylindrical coordinate system. As you know, we are discussing about the cylindrical coordinate system. We have covered the basics portion of the cylindrical coordinate system. Currently I am going to start the differential length, area and the volume concept in case of the cylindrical coordinate system. For that, let me draw the cylindrical coordinate system and as well as the cylindrical volume first. See, look at this drawing. In this drawing, I have considered a quarter cylinder. Why I have considered the quarter cylinder? Because for analysis purpose, I am taking positive x, positive y and the positive z direction. Considering positive x, y and the z direction, I have to take the quarter cylinder. Okay. Not only that, in that quarter cylinder, I have considered a small volume that has been denoted here the blue color. Okay, I have considered a small volume. And as you know, in case of the cylindrical coordinate system, this is what this position is nothing but the phi is equal to 0 degree, you know, and this is nothing but the phi is equal to 90 degree. Means phi is increasing from this direction to this direction. From x to y, phi is increasing actually. Okay, and not only that, where is the phi angle lies? That is this. This is your actually phi angle. Okay. Now, in the cylindrical coordinate system is nothing but the rho phi z coordinate system. Among the rho phi and z, the phi is here. Now let us see what is the z. You know also where is the z lies. Let me draw it. See, this total height, that is nothing but the z. Okay, this height is same as this green color line height. Okay, so don't be the misconception about that. The height of this cylinder is nothing but the z. Now what is the rho? Rho you also know what is the rho? Rho is this. This is rho. So rho, phi and z I have covered over here. Now listen to this point carefully. Whatever I am going to discuss from now. See, we have considered a small section over the cylindrical coordinate system. Now this is the section over here, and if this is the rho, this total angle is rho, I can consider this angle, this small angle, as a d rho. I'm sorry, d phi. This total angle, if this total angle is phi, then the small angle can be considered as a d phi. Not only that, if this total height is z, the small height, this height, that can be considered as dz. Okay, this can be considered as dz. So this is dz and this is the d phi. Now what will be this length? Now look at carefully. This length, whatever I have mentioned over here, this is also very simple. This length is a small portion of this total rho. This is the small portion of this total rho. That means As it is a small portion of the row, I can write it as d rho. Okay. And the last one is this length, because this small section has the three things: length, width, and height. The same thing that we have also discussed in case of the Cartesian coordinate system. In cylindrical coordinate system, we are also discussing the same thing. That is, the height we have discussed, the height of the small section is nothing but the dz, that is the small portion of this total z. The length or width, whatever you can take. If this is the length, this is the width. So let us say the length of this section is nothing but a small portion of the row. So that's why we have considered it as a d row. And the width, that's width. Now for width, there is a trick. What will be the width? See, first understand this concept. There is a concept of the circular radius. Okay. This is a concept. Concept is, if this is a center of a circle, just a minute, okay? If this is this center of a circle denoted by O, and there is the two radius, and the angle between these two lines is theta, then what will be this? You know this very carefully. And if the radius is denoted by the r, then this distance covered by this radius within this angle theta, that can be given as s equal to r theta. I think you know this formula. The covered distance, or the portion of this perimeter, whatever has been within this angle theta with respect to the center, that has been given by is equal to r theta. This is a direct formula. Okay. The same concept I am applying here also. See this point carefully. Now, this is the marked portion over here is nothing but a portion of this perimeter of this cylinder, right? This is a portion of the perimeter of this cylinder. Not only that, the covered angle is del phi. You can see for this small portion, the covered angle is del phi, right? And the radius is rho. Now, if you consider this portion, whatever I am pointing over here, if you consider this portion, that is, it has the radius of rho and it has the small angle cut, that is the del phi, then what will be the perimeter? Covered distance in the perimeter. That is nothing but the rho into del phi, just similar as a r into theta. This was r into theta. So this will be what? Radius, that is the rho over here, and the theta. For this case, this is the del phi. That's why I can write it as rho into del phi. Rho into del phi. I can write over here. Right? Okay. These are the three things that I have considered. Now, let us discuss about the differential length first. Then I will come back to the differential area and volume respectively. First of all, now let's start discussing about the differential length. Differential length. Differential length that can be given as a dl, and obviously this is a vector quantity because length is a vector quantity, right? Differential length is a vector quantity. Now look at this carefully. If I consider the differential length, I have to also consider the directions of rho, phi and z. Okay. So for that, let me put the directions first. What is the direction of rho, phi and z? I have already discussed in my last video. That is what? See, this is, oh, just a minute. The double arrow. This is the same direction as of rho. That's why it can be given as the arrow or the direction of the rho. Three directions are there: rho, phi and z. So this is the direction of the rho. Now let's see what is the direction of the z. The z direction is this. This is the z direction, same as the z. So that has been given by az, and the direction of phi. This is, see, actual direction of phi is this, because the phi angle is starting at x equal to 0 towards the y. Okay, that is above the xy plane. The phi angle is above the xy plane and it is starting from x and go up to y. Okay, so that's why the fi angle is positive. I'm sorry, fi direction is positive towards this y direction. So definitely if this is the plus fi, then what will be this? This will be the opposite direction of the plus fi, that can be given as minus fi. Okay. So now we can discuss about the differential length, because we have all these three directions: arrow, a5 and az. As we have the all these three directions, we can discuss about the differential length. So let us now discuss what is the differential length along the direction of arrow, phi and z. First of all, let us discuss what is the differential length in case of the row directions. In the row directions, what is the differential length? In the row directions, the differential length is, see, I am considering the differential length, as the differential means small. So as I am considering the differential length, that's why I will consider the small section only, not the total cylinder. The small section, but small cut on this cylinder. So in the row direction, I can write the differential length as, see, that is the d rho in the direction of arrow, right? In the row direction, there is the component what is nothing but the d rho in the direction of arrow. So that's what I have written over here. D rho in the direction of arrow. In the similar way, I can write the differential length in the direction of phi also. That is also a vector quantity. It also have magnitude and the direction. The direction is definitely a phi. Now, what is the component in the direction of Fi? Look at this carefully. What is the component in the direction of Fi? That is nothing but this. That is nothing but this. That is the rho d phi. Rho d phi is the component of the small section in the direction of a phi. So that's why I can write it as rho d phi. Okay. Now the last one, the differential length in the direction of z. As it is in the direction of the z, I can write it as az. Okay. Now in the direction of the z, that is the in the az direction, let us see what is the component of this small section. Now look at this carefully. In the direction of the az, the section is the height, the small height, that is nothing but the dz. So I will put the dz over here, that is the dz in the direction of az. Now this is the differential length with respect to or in the direction of the rho, phi and z respectively. Now if I consider the total differential length, the total differential length will be what? The total differential length will be the summation of all those three, right? So that is over here. So what is the total differential length? The total differential length is nothing but differential length in the direction of the rho plus differential length in the direction of the phi plus differential length in the direction of the z. Okay, that will be what? D rho a rho plus what? I am substituting all these three values. Rho d phi a phi plus dz is it. That is the total differential length, and this formula is very much important and useful also. You have to remember it. Okay, remember this formula. This is the differential length. Now, as we have covered the differential length, now let's go to the differential area. Okay, so differential area, it has been given by a vector quantity differential area. That's why I have written ds, not the s, ds, as it is a differential area or the small area. That's why I have written ds, and it is a area is a vector quantity, because I have already shown how the direction of the area vector has been given. The direction of the area vector is what? Direction of the area vector is nothing but the perpendicular over that surface, right? So you know that. So for that differential area, for this differential area, I have to draw the three areas first. Just a minute, give me some time. See, this is the same coordinate system, And over this coordinate system, let us see what are the three areas. See, three areas are nothing but the three exposed areas. Okay, what are the three exposed areas? Exposed areas of this small section. See, I am pointing the area over here. This is 1, 2, 3, and 4. This is 1 dash, 2 dash. This is the 4 dash. 3 dash is in the another direction. Okay. So first of all, three areas are what? That is 1, 2, 3, 4 is another area whose direction of this area vector is arrow direction, right? I have already told about the direction of the area vector, how the direction of the area vector has been taken. The direction of the area vector is nothing but the perpendicular, just like as this. This is a perpendicular, right? This is also a perpendicular. So direction of the area vector is nothing but what? The perpendicular. So if we consider 1, 2, 3, 4 area, the direction of this 1, 2, 3, 4 area will be in the direction of the row, that is the arrow. Similarly, if I consider 1 dash 1, 4, 4 dash, that is this. If I consider 1 dash 1, 4, 4 dash, this area, if I consider this area, then the direction will be in the direction of the minus arrow, right? Direction will be in the direction of the minus arrow. Similarly, see, arrow is in this direction, minus arrow is in the opposite direction of the arrow. Remember this point. Don't write the arrow in this direction. Okay, most of the students do a mistake here. Arrow direction will be the positive direction of the, I'm sorry, Fi. Fi direction is, Fi direction will is in the positive direction of the phi. Actually, don't write this as a positive Fi. This is the negative Fi. This is the positive Fi. I think you have understood that. Now, if you understood, then what will be the direction of this 1 dash 1, 4, 4 dash? That will be nothing but in the minus arrow direction, right? That is nothing but the perpendicular with this area. Okay. Similarly, for the area 1 dash 2 dash 2 1, for this area, the top area, the area in the top side, that will be for this area, az will be the direction vector of this particular area. Okay. So these are the three areas, and these three areas I am going to draw over here again. What is the first area? This is one area C. The another area is this. Another is this is another area. Okay. These are the three areas. Now three areas has the three direction vector. Let us see the direction vectors. This was one, this was one. Direction vector is nothing but the perpendicular with that area, right? Now this was what? Minus Fi. This was what? Az. This is the arrow. Okay. Now let me point these areas also. This was 1 dash 4 dash 1 4. This was 1 dash 2 dash 1 2, and this is what? This is nothing but the 1 2 3 4. Okay. Now for this area, that is 1 dash 1 4 4 dash, for this area, if I want to write the area vector, that is the bs, then what will be that? That will be nothing but the magnitude and the direction. Now you know that the direction is what? Direction is, that is minus fi. Okay, that is the constant. Now area. For area, you know that this is what? This side. Sorry, this side is what? This was the arrow. This was the arrow and this was the dz. Look at the main figure. You will understand that. See, this is the dz and this is the d-row. This is the d-row, this is the dz. Okay, the d-row here means what? 1 1 dash is also d-row. 4 4 dash is d-row means 1 1 dash is also d-row. Similarly, 1 dash 4 dash length is dz. If 1 dash 4 dash length is dz, then 1 4 will be also dz, because these are the parallel lines with respect to each other. Right. So that's why I have written this is the dz and this is the d-row. Okay. If this happens, so what will be the magnitude and what will be the area here? It is nothing but the d-row dz. D-row dz in the direction of the minus arrow. Now, for this case, for this area, tell me what is the ds? You are sure that the ds will be in the direction of what? Az. Okay, ds will be in the direction of az. If the ds will be in the direction of az, let me tell about the magnitude of the length and the width. And what will be the length? That is the 1 1 dash or the or 2 2 dash. What will be this? This is nothing but this is the d row. This side is also d row. That side is also d row. And what is this? This length is, I have already told about it. That is nothing but the rho d phi. This length is the rho d phi. I think I have already talked about it. Right? How the rho d phi has came over here. So what will be the magnitude of this area? Very simple. Rho d rho d rho d phi. Okay. That is nothing but the multiplication of these two, 0 and rho d phi. Okay. That is in the direction of the az. Now the last one, 1 2 3 4, for this area. For this area, what will be the area vector? Now you are again sure that the area vector, the direction of the area vector will be in the direction of the arrow. Now what is the magnitude? For the magnitude, you know what is this length? This length is nothing but dz, you know, and this is rho d phi. I have already told here, that is rho d phi. That is nothing but rho d phi dz. Okay. So again, I am telling you that is the direction of the area vector is always perpendicular with the same area. Okay. In this case, three areas are exposed, or the three areas in the three directions has been exposed. So that's why I am considering these three areas separately. I have shown you what is the area vector for these three corresponding area which are in the direction of the arrow Fi and Az. Okay, I think it has been clear to you. Now let me put some note over here. The same note that we have discussed in the Cartesian coordinate system also. So what is the note? First note is, you know, that is the area vector is always normal to the surface and taken away from it. That's the first note. So let me write it. Just a minute. Just a minute. The area vector is what? The area vector is always normal or the perpendicular, whatever, normal or perpendicular, the same word. Always normal to the surface. See, this is the constant for any kinds of the coordinate system. Normal to the surface and taken away from it. Okay, very important note. And the second note is, what is the second note? Second note is, let us see what is the second note. Second note is, see, there are the, in case of the cylindrical coordinate system, the three parameters are there. What are the rho? Oh, let me take in the dark color. Rho, phi, and z. These are the three parameters in case of the cylindrical coordinate system. Right, in case of the cylindrical coordinate system. Now, among these three parameters, if the two parameter gives the dimensions, any two parameters, you can consider rho phi or you can consider phi z, you can also consider rho z. The two parameters give you the dimension of the area, and the remaining parameter, the remaining one parameter, remaining parameter gives the direction. Okay. Now, what is that means actually? Don't worry, I am giving you an example. See, consider these two parameters. Let us see the rho and phi, these two parameters. I am taking these two parameters so that it gives the dimensions. Okay. So dimensions of what? The area. Area is a vector. Now you know that is the vector has the two parts. One is magnitude and one is the direction. So I am considering rho and phi, these two parameters to give the directions. So you can see over here, that is, if I select rho and phi to give the directions, then give the dimensions, that will be what? Rho d phi. Okay, rho d phi. That means the rho and phi has been used here to give the dimensions of the area, and the direction is given by the remaining parameter. The remaining parameter is what? Z. So Z is used to give the directions. That is it. That's what I have written over here. That is the dimension. And this is what? Direction. Sorry, this is the dimension. And this is the direction. Okay. Dimension, this is the direction. Okay. I think it is very much clear to you. Among these three parameters, rho, phi, and z, any of these two parameters, if any of these two parameters is used to give the dimension of the area, then the remaining parameter will be used to give the direction of the area, because area is a vector and the vector must have the two things, one is dimension and another is directions, or we can say the magnitude and the directions also. Dimension is nothing but the magnitude. Okay, so the last one parameter, that is the differential what? Volume, that has been left over here, right? Because we have talked about the differential length and differential area. Now the last one is the differential volume. And definitely this has been given by the dV, because differential volume is scalar quantity. Remember this point very much clearly. So differential volume is a scalar quantity. Just a minute. Let me box these differential areas first, because the formula is very much important. You have to remember it. Okay. So differential volume. Oh, so dirty handwriting I have. Just a minute. And volume is what? Volume is a scalar quantity. That's why I have written dV over here. And that is the scalar quantity. Yeah. Now, differential volume. Okay. Now the differential volume is what? A scalar quantity. Now you know that the volume of a section can be given as the multiplication of length, area and width. In this case, the same thing will also happen because this is the small section, right? This is the small section, and and the length into width into height will give you the total volume of the small section. Now, what is the length? Length is nothing but the d rho. The width is nothing but the rho d phi, and the height is nothing but the dz. So multiplication of the d rho d phi, and the dz will be nothing but the differential volume. So I can write it over here. That is the dv is nothing but the d rho, that is nothing but the length into rho d phi, that is nothing but the width into dz. Okay, and from here I have organized it a little bit. That is what. See, I can also write it in the organized way. That is nothing but the rho d rho d phi dz. Very easy. Rho d rho d phi and dz. And it is a very important formula that you have to remember it. Okay, important formula that you have to remember. So that is the differential volume. And not only that, this is all about the differential length, area and the volume in case of the cylindrical coordinate system. So there is the another approach that we can use to remember only the formulas, but for the concept you have to go through these derivations, little bit of the derivations. So that's not too much hard. This is not a rocket science. So you have to just do a little bit practice about it. And another method that I am talking about, that is the to remember the differential length, area and the volume formulas. I will talk about it after the completion of the total coordinate system. There is another coordinate system, the third, that is the spherical coordinate system, that has been left over here. In my next video, I will start the spherical coordinate system. I have covered the cylindrical coordinate system totally over here. Okay. So see you in the next video. And from the next video we are starting the spherical coordinate system, and please do practicing this all derivations and these all concepts, so that you will be it will be much more easier to you. Don't just by watching this, but do it in your pen in the paper also. Okay, so that's all for today guys, and we will meet you soon. Thank you and bye bye.